Hello, and welcome back to Homework Help for Math 2. Today we're going to be looking at Unit 1, Lesson 5, Quadratic Functions, the Tortoise, and the Hare. The directions in the Ready section ask us to identify which of the following representations are functions. If the representation is not a function, state how you would fix it to make it a function. So, question number 1. This mathematical relationship, called D, is given to us as a series of XY pairs. So XY, 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 XY. Now, in order for a relationship to be a function, it means that for all inputs, for any given input, we can have at most one output. In other words, it means that when we plug something in, typically a number, when we plug in that number, we should be able to predict with 100% certainty what the output is going to be every single time, and that output should not change. So whatever it is, and if you plug in an input and you get multiple possible outputs, that is no longer a function. So here with number 1, what we have to do is we have to check and see, all right, well, for the first example, or for the first pair, it's 4, -1. So when you plug in a 4, you get a -1. Now, if I go and check all of my other pairs here, none of my other pairs have 4 as the input. So I'm looking through and I don't see any other pairs where 4 is the input. So far we're good, right? Because that first point, you plug in a 4, you get a -1, and I don't see any conflicting information that would change that because there's no other pairs here where 4 is my input. Looking at the next pair, I see 3, -6. Again, this is telling us that when you plug in a 3, you get a -6, and as long as I don't see any other examples of plugging in a 3 and getting something other than a -6, this would check out as a function, and I'm not seeing any other 3s as inputs. So again, so far so good. The third pair is 2, -1. Again, that means that when I plug in a 2, I should expect to get a -1 every single time. So I'm looking, and I notice, so that's the one that we're talking about, and then I notice here at the end. Notice that the 2 that I just circled, well, the first one says you plug in a 2 and you get a -1. The last one says you plug in a 2 and you get a 5. That's no good. So that's going to be a problem if we want this thing to be a function. So our answer for number 1 is not a function. Now, the directions said if something is not a function, have an idea as to, all right, well, how do we fix this so it is a function? So to make this a function, we need to modify or delete either 2, -1 or 2, 5. That's the problem here. Real quick check. The 1 and 2 is fine. The 1 and 2 is fine, and the 0 and 4 is fine, right? But it's the two different inputs. It's the same input, but two different results that's preventing this guy from being a function. Number 3. So in this problem, we're given another mathematical relationship. This time we're given a graphical representation of it. And again, this idea of what makes something a function or not doesn't change. And it's saying whenever you have any given input, you should have at most one output. So in this context, my inputs are all of my x's. Right? So, for example, if I plug in let's say I plug in a -1, right? Well, what do I get? Well, I can see here that this point right here, right? This point is -1, comma, what is it? 5, I guess. So this is saying when you plug in a -1, you get a 5, and I don't see any other, there's no other dots, there's no other dots on this vertical line here. So when you plug in a -1, you're going to get a 5 every single time. If I plug in, I don't know, if I plug in a 2, right? 2 is right about there. I get that point. I get that point right there, which is maybe like a little bit below 0, right? All of this is to say, when you have a graph and you are trying to determine whether that graph represents a function or not, we can use something called the vertical line test. You may have heard of this before. The vertical line test asks us to, take our writing instrument, our ruler, whatever you want, and sort of run it over the graph vertically, right? So it's like see if I can do this here. So, if this is my vertical line, okay, what I want to do is I want to take it and I want to run it over the graph, right? I want to do this, like what I'm doing right now, right? I want to take and I want to look and I want to say, all right, as long as this vertical line, as long as it does not intersect the graph twice, I'm fine, right? This is, in fact, a function. And you can see here that the entire time, as I'm going from left to right, my vertical line, it only ever intersects this graph at most once, right? Once, and then it gets here, and it doesn't intersect at all. But if you were to continue this graph, it would be down this way, right? So this graph passes the vertical line test, and because it passes the vertical line test, that tells us that number 3 is a function. So number 3, function. Number 4. This time we are given a table of values, and we're using function notation this time. So we'll see whether that's warranted or not for this being a function. So our inputs are -12, -8, -6, and -4. And what this first I guess technically the second column says, it says when you plug in a -12, you get a 25. And I'm not seeing any other inputs of -12 that result in anything other than a 25. So far we're good. The next column says when you plug in a -8, you again get a 25. Well, as long as I don't see any other inputs of -8, I'm actually fine. It is not a problem, okay? It is not a problem that I get 25 twice. That's okay. It is okay for my outputs to repeat, to be identical with given inputs. That is not a problem. What is a problem is if I have identical inputs that result in different outputs. That would be a problem. But I don't see any other -8s here as inputs, so we're good. Next column is we plug in a -6, and again we get a 25. So this is not a super interesting relationship. I just seem to be getting 25 no matter what my input is. But that's not a problem. That doesn't make it not a function. And again, I don't see any other inputs of -6, so we're good. And yeah, -4 again gives us a 25, but I don't see any other contradictions with any other. I don't see any other inputs of -4. So we end up getting the same output every single time. So this is kind of a silly function. It's not really doing much. It's just spitting out a 25, but it is in fact a function, right? We're not maybe, yeah, we're not judging the function, right? It's doing what it's doing. So next question is 5. All right. So question 5, we are given a graph. And as we saw with question number 3, in order to tell whether the graph of a relationship represents a function or not, we can use something called the vertical line test, because that's going to tell us, do we ever have a situation where there's an input that results in 2 different outputs? And you can see here that as I'm kind of going back and forth here, there are multiple instances of where this vertical line intersects this graph twice, right? So, for example, if I just stop right here, okay? If I stop right here, and I'm going to get rid of the line, but just sort of remember where we're at. It looks like we're at, well, yeah, we're at whatever that input is. It's a weird scale here. 2, 3. Yeah, it's some decimal, 1 point something. But you can see that there is one. Let's make it easier. Let's just go with 2. So when we plug in a 2 right here, one output is up here, right? So that looks to be about 1, I guess. So it would be like 2. So this point right here is something like 2, 1. But then when I plug in a 2, I also end up down here, right? That's also what happens when you plug in a 2. And down here it's like 2, and it's like negative 1 point something, 1 point, I don't know, 8. The actual number itself doesn't really matter. But you can see here that when you plug in a 2, we get 2 different results. And that alone is enough to make this not a function. But you can see here that there's lots and lots and lots of examples that we could have chosen. So the answer for 5 is that not a function. Now, because it's not a function, we're also expected to sort of identify, all right, well, what would we need to do in order to make it a function? And to make this a function, we could eliminate one of the pieces of the graph. So we could see here that theoretically, if we were to just sort of like eliminate that bottom piece entirely, and if we were left with just this piece, that would be a function. So that would be one way to fix it. Question 6, again, we have a graph. I'm going to get my whatever it is that I'm using as my vertical line. If you're doing this by hand, you could just use your pencil, pen, erasable pen, because it's math. And you can see here that as I take my vertical line and sort of span this graph, I am not seeing any instances where this vertical line intercepts this graph more than once. Again, it is okay if it doesn't intersect at all. That's not a problem. What is a problem is if the curve were to intersect this vertical line more than once, and it only has to happen like that, like intersecting twice, it only has to happen one time. And if it does, then it's automatically not a function. But I don't see that happening. So 6 is a function. Moving on to the set section. The graph in figure 1 shows the time in minutes on the x-axis and distance in miles on the y-axis for cars traveling in the same direction along the freeway. The graph for car A is a straight line. The graph for car B is a parabola because it is a quadratic function. And there's our graph. Question 7 asks us, which car has the cruise control on, or in other words, is maintaining at the same speed? How do you know? So, like I said, we're told that car A is the line and car B is the parabola. So, with car A, because we're looking at, we are comparing distance and time, right? So use different color there. So if you think about what's happening with the slope of this line, let's say we want the slope between, it doesn't really matter. Let's say this point, and we'll say that point right there on this line. Well, my rise is going to be the distance, right? So it's going to be this. Looks like it's about maybe 5. And then the run is going to be like this. Something like that. And that's going to be, what, 1, 2, 3, 4, 5, 6. And if you think about what these numbers represent, well, 5 is miles, and 6 is minutes. And so if we want our slope here, it's going to be rise over, oops, over run, which is going to be miles per minute. Miles per minute. So this is speed. Right? Miles per minute or miles per hour or kilometers per hour, right? If you have distance over time, that is a unit of measurement of speed, 60 miles per hour, right? 5/6 miles per minute, right? That's what this is. And so because car A, because this distance is a straight line, it has a constant slope, as a constant rate of change. And when you're doing time, when you're doing distance over time, then your rate is speed. And so our answer for 7 is car A has cruise control on. Because the rate of change, speed, or slope, in this case, is constant. So when we're comparing car A, looking at distance over time, that rate does not change, and in this context, the rate is speed. And so, if one of these cars has cruise control on, it is car A. It is traveling at the same speed this entire time. Okay. Number 8. Which car is accelerating? How do you know? All right, well, by process of elimination, we basically know this is car B, right? So if car A, for the reasons that we just discussed, has their cruise control on, and we're only talking about two cars, well, clearly car B has to be the other car. But in terms of like why that's happening, if I get rid of all the other stuff here, with car B, the graph here, as we're told, it's a parabola, and so the rate of change, in this case the speed, is not constant. If you were to take the slope from say here to here, you're going to get a very different slope compared to here to say there, right? So that line is going to be a different slope than that line, right? So the slope here is changing, and as time increases, as you go to the right, the slope of the parabola at any given point is increasing, right? So what's happening here is, we'll just go ahead and write it out. So car B is accelerating. Because the rate of change, again, in this case, the speed or the slope, is itself increasing. So in the beginning, the slope of the parabola is pretty small, but it increases over time, and it just continues to increase. Number 9, we're going to have to scroll down a little bit here. So for number 9, identify the interval in figure 1 where car A has gone farther than car B. All right, well, for this one, we just have to sort of take a look at our graph. Let me clear out some of these random scratch marks here. All right. So we're looking for what is the interval of time where A is farther than B. So my y-axis here represents distance. So basically what we're saying is, what is the interval of time where the graph of A is visually above the graph of B? Because again, our vertical distance here, or our vertical axis represents distance. So if A is higher, it means it is farther than car B. So if we want to identify that, then it looks to me like at so at 0, car A pulls out in front immediately, right? Car B is starting off a bit slower, right? So car A, as soon as time starts, and car A is almost immediately in front of car B. And that continues, right? This entire time, A is above B, but B is starting to catch up until eventually we get to about there, right? At that point, when you go to the right from that second dot, you can see that the parabola, car B, is actually above car A. So we basically want the time interval between the two red dots. Well, here, time is 0. And then here, well, it's between the two boxes, so time is approximately between, 11 and 12? So we'll say it's approximately 11.5, right? That's our answer. So just go ahead and write it. So from 0 to 11.5 seconds is what we're looking at. So between time equals 0, I'll even say from t equals 0 to t equals 11.5 seconds. Or if we want to use interval notation, in interval notation, we're talking about 0, comma 11.5. We only have to do part A for number 10. Number 10 says, the graph of the speed of a third car, car C, which has an exponential relationship, right, so now we're talking about an exponential relationship, is now shown in the graph. See figure 2. All right, so C is the new guy right there. All three cars have the same destination, so they're traveling in the same direction. Before we get to 10A, I would encourage you to just take a look at this graph and sort of just absorb what's happening with C. C starts off real slow, right? C is like kind of doing nothing for like minutes, right? I mean, look at 5 minutes. It's like barely done anything, right? In fact, it isn't even really till like minute 8 that he even really starts moving like at all. And then he goes pretty fast. that's what happens with exponential functions. So we only have to do part A. If the destination corresponds with a distance of 12 miles from the origin, which car do you predict will arrive first, and justify your answer? So 12 miles. They all start at 0, and 12 miles is right here. All right, that's 12. And so we're talking about, let's see, will it actually do a straight line for me? There we go. Nice. So we're talking about that right there. Right? And again, notice that our x-axis is time. So our x-axis is telling us, how long does it take these cars to go a certain distance. And what I see here is I see there's an intersection there, there's an intersection there, and there's an intersection there, right? And those are the 3 times when cars A, B, and C, in some order, have traveled 12 miles. So the first car, based on time, the first car to travel 12 miles is the first green dot. And you can see that that is along this line right there, right? So, and that is car C. So car C is the first car, even though it did nothing for like 8 minutes, at roughly 12 minutes-ish, 12, maybe 12 and a half, we'll say. At roughly 12 and a half minutes, car C has traveled 12 miles. And then the second green dot belongs to car B. It's on the parabola. And that seems to have taken him or her about 13 minutes. And then the last car to travel 12 miles is car A, the straight line. And that seems to have taken them roughly 14 and a half minutes. So our answer for 10A is car C. So we're going to say our prediction is car C, and our justification is that car C travels 12 miles in about, we'll say 12 and a half minutes. Looks maybe a little bit less, but it's okay. Whereas car B takes about 13 minutes, and car A, just a little bit smaller so we can read it. And car A takes about, we'll say 14 and a half minutes. And finally, in the Go section, the directions here say, state the domain and range of each graph. Use interval notation where appropriate. And for number 13, we're not given a graph, or it's on the next page. So I am not going to record my answers here. We're just going to see next page. So, all right. So this is 13. And we'll just retype domain and range. We'll just do it over here. All right, so domain, I might as well use the, sure. So we got domain and we got range. All right. And we'll just record our answers right there. A little bit of extra space. All right. So the domain is what are all of the possible, or what are all of the acceptable inputs into this function, right? So we have a graph of a function, relatively basic straight line segment rather, and we're looking for, all right, well, what are all of the possible x values that are included in the graph of this function? So if we're looking at x is my, my horizontal numbers. And when I look at this graph, it looks to me like the x value that is farthest to the left is -1, because the graph starts, here, and my lowest x value in this case is -1, and then the graph ends here, which corresponds to a +1. And so my domain for this function is all of the numbers, all of the values between -1 and 1. Now, because the dots that I've circled are filled in, they are solid, what that tells us is that it also includes the -1 and it includes the 1. If those dots were open or hollow, it would mean that it includes all of the numbers up to the -1, but not actually the -1 itself. But we don't have to worry about that because these dots are filled in. So our domain, now because our domain includes the -1, if we're going to use interval notation, it means we want to use a bracket. All right, so a kind of a straight bracket there. And that tells us that it includes the -1. And then our upper bound is +1. And again, we're going to close with a bracket because that tells us that it includes our endpoints of -1 and 1. If it didn't include the endpoints, we'll see that in another question. Meanwhile, the range is the exact same thing except it deals with y. The range is what are all of the possible y values, or what are all the possible outputs of this function. And it's the same endpoints, but now we're just focusing on the y values. The smallest y value is -1, and it includes the -1. The largest y value is 3, and it includes the 3. So our range in interval notation is bracket -1, comma 3, close bracket. That tells us that it's all the numbers between -1 and 3, including the -1 and including the 3. Okay, 14. So for 14, same question, just identify the domain and the range. So looking at um, this graph, unlike 13, 14 actually continues. It doesn't necessarily have a start and a stop. Because we are allowed, actually, not only are we allowed to assume, we kind of have to assume that this graph continues in both of these directions, right? So we're just seeing this piece of this graph, but it does continue to the top left and the top right. So the domain, again, is asking us what are all of the possible x values that could serve as inputs into this function. And because this graph continues to the left without end, and because this graph continues to the right without end, our domain is every single number, every single real number, right? And so when we're writing our domain, I'll just write this freehand. It's going to be, our lower bound is going to be negative infinity, right? We can go all the way down to our our lowest possible, I don't want to say number because infinity is not a number, it's a concept, but it means that we can go as far negative as we want, right? Negative 3 trillion and billion, whatever, right? We can go all the way to the left on the number line that we want, and that is still going to be in the domain of this function. And likewise, because we keep going to the right, our numbers can become impossibly huge, all right? And it's all fine for the domain because we can have any number we want, and so our upper bound is positive infinity. Now, like I said, infinity is not a number, it's a concept, and we can never, in this context, you can never actually get to infinity. So with interval notation, you want to use parentheses here. You want to use curved grouping symbols, not the brackets, because that just sort of, it's kind of a technical thing. It just says, all right, you're not actually including infinity itself in the domain, but you do get to use basically any number up to that, which is every real number. So our domain is parentheses, negative infinity, comma, infinity, close parentheses, and that is expressed in interval notation. For the range, we're going to see something similar but not exact. And the reason is because, remember, the range is dealing with the y coordinates. And with the y coordinates, notice that we do have a lower bound here, right? This graph, the lowest possible y value is -1, right? There's nothing down here, right? So we do have a lower bound, but again, this graph continues up and then up again. Right? You only need one of those arrows for the range, but we have a lower bound, but we don't have an upper bound. And our lower bound includes the -1. And so the way that we're going to write that, our lower bound is going to have a square bracket, right? And -1. So that tells us that it includes the -1. Our upper bound, quote unquote, doesn't exist. And when that happens, we can just say, all right, we'll go up to, up to infinity. Don't include infinity. So you need a close parentheses there, not a bracket. But other than that, feel free to use any number you want as long as it's between -1 and infinity, including -1 but not including infinity. And that's our range. Next question was 16. Again, we're looking for the domain and the range. So our domain here, our lowest possible x value is right there. right? So that is the point on this graph where there's nothing over here, right? This is just blank space. So our lowest possible x value is that right there, which is -4. Our largest x value is right there. And again, there's nothing there to the right of that. So that does not work. Want to be careful. This is not a function, so I don't want to call this a function. This is a mathematical relationship. It's called an ellipse, but this is not a function. So I want to make sure I make that clear. So our sort of endpoints here for the domain, it includes -4. So we're going to have negative. Oops, change that back to that. So our lower bound is -4. Our upper bound is 2. And we can use a square bracket on the -4 because it includes the -4. And we can use a square bracket on the 2 because it includes the 2. The range, we're going to do the same exact thing except in the y direction. So for our range, our lowest y value appears to be right there, which looks like it's -2, and our greatest y value appears to be right there, which is +2. And so our lower bound for the range was -2. Our upper bound for the range was +2. It does include the -2, so we're going to use a square bracket. It does include the +2, so we're going to use a square bracket. So our domain is open bracket -4, 2, close bracket, and our range is open bracket -2, 2, close bracket. For 17, our domain, our lowest x value in this graph appears right there at -6, and our largest x value appears right there at +2. So there and there. So like I said, our lower bound for the domain is -6. Our upper bound for the domain is 2. And it includes the -6, so we're going to have a square bracket, and it includes the 2, so we're going to have a square bracket. So our domain is open bracket -6, 2, close bracket. And also, just to clarify, I don't think I said this in the earlier questions, but this interval notation tells us that it's just telling us our bounds, but it also includes all of the numbers between them, right? So in this example, it includes -4, -2, 0, 1, 1/2, the square root of 2, which is an irrational number, right? It includes all of the numbers between -6 and 2 as well. For the range, so our range is all of our acceptable y values, and we have a horizontal line in this case. So with a horizontal line, your y values don't really change. All of our y values are -2. So you can spend all day on this line here picking points, and every single point on this line has a y value of -2. Right? You plug in a 2, you get a -2. You plug in a -4, you get a -2. You plug in a 0, you get a -2. So it's not a super interesting function because the input is almost irrelevant. It's like, all right, I don't really care about your input. You're going to get a -2 no matter what the input is. It is still a function. The range is just what are all of your acceptable y values. Well, the only real y value here is -2. And it includes -2, but it is both the lower bound and the upper bound. So I hope you like -2s because that's all you're getting with number 17. That's your range. 19. The graph of 19 is refreshingly simple. This is a linear function. Our good friend looks like it has a slope of about 3. Not that that's relevant to this question, um, but again, the domain is what are all of the possible inputs? What are all of the possible x values? Well, again, with a graph like this, we can and should assume that this graph continues on, right? That it only really ended because they ran out of space, but that it does in fact continue. And so if you think about what's going to happen at the bottom of this graph down here, right? Well, it's going down, but it's also going to the left, right? And because it's going to the left, it means that these x values are just going to continue to get negative, right? We're talking about x in this case. So because the bottom part of this graph is also going to the left, we're never going to run out of negative numbers. It's just going to continue on to the left indefinitely. And likewise, up here, it's going up, but it's also going to the right, and so the numbers are getting more positive, they're getting larger. And again, it's not going to stop. Like, it's just going to continue to go. And so our domain, our lower bound, is essentially that there isn't one. And when there isn't a lower bound, we can say that, all right, well, that means that the lower bound is negative infinity, which is not a number, but we're going to treat it kind of like a number in this context and just say, like, all right, well, that's our bound. We cannot go past negative infinity, which is obvious. And then our upper bound, again, it, quote, doesn't exist. And when it doesn't exist, we can say, all right, well, then you just go to infinity, and you'll never get to infinity. But if you were, stop there, but you won't. And again, because you never actually get to infinity, we want to use parentheses here, not brackets, because brackets would say that it includes the number, and we're not including infinity in the domain. But other than that, it's just saying, all right, go nuts. You can use any number you want. That's in the domain. And that's that. Range is extremely similar. Range is the same thing, but with y. And you can see here, like we said already, this graph is going down without end, without bound. And it's also going up without end, or without bound. And so for our range, we can just keep on going. We're not going to stop until we get to negative infinity, which is never going to happen, so we just don't stop. And then our upper bound also, quote unquote, doesn't exist. So let's just say keep going until you get to infinity. And we're not going to include the infinities, and so we're going to use parentheses. But that's our range. So the domain and range are all real numbers. Any number that you can possibly think of that's a real number can serve as both an input for this function, so it's in the domain, and also a result of this function, and so therefore it's in the range. Number 20, we're not going to write things here. We're going to write them on the next page. So this is 20. I'll just type it, or I'll just write it this time. Domain and range. Oof. Okay. There we go. So domain and range. So this is unlike any of the other questions that we've seen in this section, clearly, because unlike every single other question that we've seen, number 20 is not continuous. 20 has some pretty large gaps, and it's only including points, not a line or not a curve or whatever, right? We just have a series of points here. So we actually cannot use interval notation this time, because with interval notation, you establish your lower bound and your upper bound, but then it also includes all of the numbers in between that. Whereas here, we are not including the numbers in between the dots, because if we were, they would be in the graph, and they're not, so we can't include them. So we actually cannot use interval notation here, so we'll just express our domain and range as a set. So with set, we have our fancy brackets, fancy curly brackets, whatever they're called. But again, our conceptually, the domain doesn't change. The domain is what are the acceptable inputs? What are the acceptable x values? So x, as always, is on the horizontal axis, and let's just identify what they are. So our scale here, 0 to 5. So it looks like each box is 1. So that's nice. It's a really easy scale in both the x and y direction. So our lowest x value is here, and that appears to be -1. And then it includes this guy, which is 0, this guy, which is 1, this guy, which is 2, and this guy, which is 3. So for our domain, we are just going to list each one of these elements that's going to comprise this set that is our domain. So our domain includes -1, 0, 1, 2, and 3. And that is it. You have exactly 5 choices for your input. You can plug in a -1, you can plug in a 0, you can plug in a 1, you can plug in a 2, or you can plug in a 3. That's it. You cannot plug in 1/2. You cannot plug in 2 2/3, right? It has to be one of these 5 numbers. Likewise, for the range, of course, is y. My lowest value for the range, once again, is down here, and that's labeled as -5. Then there's here, and if each box is 1, then this is down 2, so this is going to be -2. Then there's here, which is a +1. There's here, which is a 4. And there's here, which is a 7. So for our range, again, we cannot use interval notation, so we'll use set notation here. And our acceptable outputs, our acceptable y values, well, our lowest is -5, and then we can also get -2, we can also get 1, we can also get 4, and we can also get 7. So this is saying, basically, I hope you like these 5 outputs, because that's all you're getting from this function, right? -5, -2, 1, 4, and 7. Those are all of the possible results. When you plug in something, you'll get one of these 5 numbers, and so that is the range.